One of the most significant recent insights into the biology of aging is the role of cellular senescence, the process by which cells stop dividing and enter a dysfunctional but metabolically active state. These so-called zombie cells don't die when they should. Instead, they persist in tissues and begin to secrete a range of pro-inflammatory and tissue-degrading molecules, collectively known as the senescence-associated secretory phenotype, SASP. While cellular senescence is a natural mechanism that helps the body prevent cancer and manage tissue repair in youth, its chronic presence over time becomes increasingly harmful. The accumulation of these cells contributes directly to the slow breakdown of tissues, the onset of chronic inflammation, and the functional decline that defines aging across virtually every system in the body. In youth, senescent cells are typically cleared quickly by the immune system. They arise in response to stress, DNA damage, or cellular wear and tear, and their early removal is protective. But as we grow older, immune efficiency declines and the body's ability to eliminate these senescent cells diminishes. What was once an elegant system of quality control becomes a major liability. The cells begin to pile up in the skin, joints, vasculature, lungs, liver, and even the brain, where they emit inflammatory signals that disturb nearby healthy cells. This local disruption can spiral into systemic inflammation, a chronic, low-grade immune activation sometimes referred to as inflammaging. This steady inflammatory pressure contributes to a wide array of degenerative diseases including atherosclerosis, osteoarthritis, type 2 diabetes, Alzheimer's disease, and sarcopenia. What makes senescent cells uniquely damaging is that they don't just sit idly in tissues. They actively sabotage the environment around them. Their secretions include cytokines, chemokines, matrix metalloproteinases, and growth factors that degrade the extracellular matrix, recruit immune cells unnecessarily, and encourage nearby cells to enter senescence themselves. In this way, one zombie cell can spark a chain reaction, spreading dysfunction like a slow biological contagion. Over time, this leads to the thinning of skin, the stiffening of blood vessels, the scarring of lungs and liver, and the gradual erosion of tissue integrity in muscles and organs. Despite their destructive tendencies in aging, senescent cells originally evolved as a protective mechanism, acting as a barrier against uncontrolled cell growth and tumor formation. This is why senescence is often triggered by DNA damage or telomere shortening, hallmarks of potential cancerous transformation. However, this protective role comes with a steep cost when these cells overstay their welcome. It's not the presence of senescent cells that's inherently harmful, but the persistence of them, and the failure of clearance mechanisms that once kept them in check. Recent breakthroughs in biotechnology have begun to target this issue directly. Senolytic drugs, which selectively remove senescent cells, have shown promising results in animal studies. Mice treated with senolytics exhibit fewer signs of frailty, improved physical function, and longer health spans. In models of age-related diseases like osteoarthritis, intervertebral disc degeneration, or neurodegeneration, clearing senescent cells often halts or even reverses disease progression. This represents a substantial shift in how we view aging, not as a passive, unstoppable decline, but as a modifiable process driven in part by cellular byproducts that can be actively removed. Even without pharmaceutical intervention, understanding the role of cellular senescence empowers more informed lifestyle decisions. Factors such as smoking, excessive UV exposure, poor diet, chronic stress, and environmental toxins can accelerate cellular damage and promote senescence. Conversely, habits that support DNA repair, antioxidant defense, and immune function, such as regular physical activity, plant-rich diets, fasting mimicking strategies, and adequate sleep, may help delay the buildup of senescent cells or enhance the body's natural clearance mechanisms. The growing recognition of senescent cells as culprits in aging reframes many of the common signs of getting older, not simply as inevitable, but as the byproduct of cellular dysfunction that we may one day be able to control. It invites a future where treatments do not merely patch up symptoms, but intervene at the root. While aging will always be a multifaceted and complex process, the identification of cellular senescence as a key player provides a new lens and a new sense of optimism for how we approach the second half of life. The dream of aging not just longer but better is no longer a fantasy. It is increasingly within reach.